Hi everybody and welcome to the bonus video for Trio 2. Today I want to talk about a subject called tries, and it's a type of tree as you'll see in a second. And let's just get started. So we've talked about ABL trees and other kinds of binary trees, but we haven't really gone further. And as you will soon see when we start talking about graphs, we will talk about sort of the bigger picture where trees are just a tiny piece of it. But between trees and graphs, there aren't more than just binary trees. In fact, there can be n-nary trees, where n being the number of nodes, or sorry, children that I can have. So binary trees have 0 to 2 children. Technically, unary trees, also known as linked list, have 0 to 1 children, right? Usually, the only one that has 0 children is the last node in the linked list, which can be just the first node if it's just one node in the entire tree. So really it only starts getting exciting once we talk about binary trees. There can also be potentially a ternary tree, which means that it can have anywhere from 0 to 2 children. So you could have something like this. You could also have any binary tree. Any binary tree is technically a ternary tree. It's just not taking advantage of that third potential child. But anywhere here, I could add it like that. And so ultimately, you can have n-nary trees. And typically, it's pointless to call a binary ABL tree a ternary tree if you're never going to have that third branch. So typically what you end up doing is you look at the child or the parent, or you look at any node of you look at the entire tree and find the node with the highest number of children. And suppose that you have a really, really big tree. Like this. In this tree, we have nodes with no children, such as these. We have nodes with one child, such as these. Or not that one, not the last one, but which other one? That's it. I think those are all the ones that have one child. And then we have, let me mark this one, this one, this one. So this is 0 children, 1 children, and then we have 2 children nodes, which are going to be this one. Let's make that bigger. We have this one, this one, this one. I just found another single childless node, which is this one. And then we have nodes with, or here, one more with 2 children. And we have one more node here. And that one actually has 3 children. So because this tree, the node with the highest number of children is 3, we could call this a ternary tree or higher. But I would stick with ternary because there's no point in calling it like a 4-nary tree when there's just 3 nodes, right? You can't call it a binary tree or a unary tree though. But if this node was gone, or at least if we lost one of those children here, if it looked like this, then I would rename this into a binary tree because there's no need to call it a ternary tree. If somewhere here though, there was maybe a node that had 4 children, then I'd have to call this a 4-nary tree. Okay, so now that we've kind of clarified that, let's talk about the tries data structure. So far we've talked about storing entire words in an ABL tree or in a binary search tree, but I'd like to offer you the concept of storing not just words in a tree, but individual letters that eventually form a word. So suppose that I have the word cat, meme, car, and me that I want to store in a tree. And I want to store them in a character by character basis. Well, one of the things that I can do is I can have a root which has potentially nothing in it. So that's just the empty set. So no word. And then from there, I can create branches based on what letter I have to print next of the possible words that I have in my universe. So in my universe, I have 4 words and potentially the empty set. So that means that in this universe, there are no dogs, there are only cats, memes, and cars, and myself. So what I can do is I can notice that all my universe has C's and M's as the first letter that they have. So therefore, I can create a node with 2 children where I have C and M as the children of that node. And from there, for the nodes that have C as the first letter, you can notice that the second letter is always going to be A. So then I can make a children here with the letter A in it. On the other hand, once I do get there, I can see that the third letter of the words that start with CA is going to be either T or R. So I can put a T or an R in there. And then on the side of the M, I can see that the second letter is always an E. And then it's an optional that I can go from there to the M and then again to the E. Why I say optional? Because technically me is okay. So here's the thing. As I have it now, if I was to ask you what words are in my universe, the way that you would do this is you would traverse the tree from the root all the way to the leaf nodes. And if you get to a leaf node, that means that it's a valid word in our dictionary. So if I ask you, do we have the word car in our universe? All you have to do is you have to traverse the tree, starting from the root, see if there's a C. Yes, there is. Is there an A? Yes, there is. Is there an R? Yes, there is. Okay, are we in a leaf node? Yes, we are. So then we can say that car is effectively in our universe. Okay, what about the word cow, like C-O-Y, C-O-W? Well, we can start by, again, going to the root. We see there's a C, but then we see that there's no O. Because there is no O, and we can't traverse the entire word, we can say that cow is not part of our universe. Okay, this works for me, but what happens with me? With me, it was part of our universe because we inserted it and we saw that. But when you get to me, it's not a leaf node. And so now you run into a situation where you're like, well, me is not part of the universe, but it was. So how can I improve this try to allow words that are part of other words to be accepted? And so I can go ahead and introduce the idea of accept states. So I can create a node, a child node that is like an accept state for whenever things are accepted. So for example, when I have car, in addition to it being a leaf node, I can go ahead and say that any leaf node is accept state but also any node with accept state. So I can create a node called accept that I'm gonna go ahead and say is a check mark. Can use a wildcard character or something. In fact, let's just go ahead and use a $sign. The $sign signifies accept. So now me has a child node, but you don't actually print out the $sign. It's just an accept state. And now we went ahead and made it so that any leaf node can accept it. So now me is still a leaf node, car is a leaf node, cat is a leaf node. The empty state we can just guarantee is acceptable by putting that there. If you don't want it to be acceptable, then it's just a temporary node. And finally, me, when you get here, you can see that it's acceptable because there is an accept state coming off of it. If you want to make your life easier implementing this, you could just make all of these accept states too, like into that, but I just stick with it being a leaf node as well. What you don't want to do, and I mean, conceptually you don't want to do it, but programming wise, it's very easy to do, and I actually would recommend it, is any node that is acceptable, you have one accept node with some address, and then you just point all of them to it. So like this one, you would let's get that out of the way for now. You would point there, and then that actually would be the best way to implement it. However, with trees, you never want it to be two parents that have a same child. You don't want that. You don't want it to be shared. That's graph land. We're gonna get there. We don't want to do it now. So that's why, from a conceptual point of view, you don't want something like this. You want them all to be individual dollar signs. However, from an implementation point of view, it's perfectly fine to do. So really, you want these all to be unique. Like that. Okay? So, why do this? Well, it turns out that it's a much more efficient way of storing text and accessing whether text is valid than other methods that we talked about. So, not only that, but notice that in both of these main branches here, when we're doing car or cat, we're only storing one instance of C and A, which means that we've saved two characters, two car values per se, or two nodes, than if we would just make this into a massive linked list of just every possible word coming out. So like if we had something like this, so we had car, and then we had cat, and then we had meme, and then we had meme. This is wasteful, and this is wasteful. We can eliminate this much space if we merge them together at the cost of having to introduce the idea of the accept state, because otherwise every single leaf node would be accept without a doubt. And so the real win here is space, but not just that, but being able to search quickly. If we have this version here stored somewhere, which could be an array with 4 things, you know, if they're alphabetized, then yeah, you could use binary search, and you could potentially find it in log n time. But here, you know, you can find it in log n time, but log n is not the size of the list, it's the size of the word. So whereas when you have a array of words, so let's say we sort these, it becomes car, cat, meme, or meme, and me. If we sort that out, then we can identify if car is a valid word by using binary search, and that's going to take log n time. And this is important, n is the size of the universe, meaning the size of the total number of words that we have. Using a try, we can identify whether a word is valid in log n time, but log n here is the height of the tree. I lie, sorry, not log n time, sorry, n time, n is the, because it's not balanced, my bad, my apologies there. You can identify it in n time. So you're like, okay, I can use binary search and find it in log n time. Why would I ever want to use a try? Because here n, again, is the number of words. Regardless of the size of the word, which doesn't matter, is the number of words. Here is the number of letters. So your n is going to be the biggest possible word that you have. So the biggest word that we have is meme here. So here it's 4. And it turns out here it's 4 as well. However, That's because we have a very small list. But let's say we had 300 um, 300 words, and the biggest word was 8 characters long. Okay, so 300 words, 8 characters long. Okay, this is gonna take log of 300. That's like, I don't know, 10 here. Quick Googling. This is being recorded sort of live, so log 2 of 100. It's basically the powers, but I can't think. It's early. 8 something, so let's just say 9. So 2 to the 9th is basically 300. So I was close when I said 10. So I'm guessing, so 10 must be 512 then. Or sorry, 9 must be 512, and then 10 is 1024, and then 8 is 256. You're a CS person, you probably know these by memory, unless you don't, like I. So anyways, 9. So that means that in 9 potential comparisons, you can identify that. Okay? Over here, it's going to be O of 8, which is the size of the biggest word, right? But here's the thing. You're like, that's very, very close. True. However, and then this is the worst case. The best case here is typically also O of 1, which could be here if it's the first word's acceptable and whatnot. But let's go ahead and boost this to 3,000 words or 30,000 words. This is going to go up. Not too much, but it is going to start going up. This will remain the same as long as the size of words don't increase. And it turns out that on average, in English at least, not other languages, the size of the biggest word is typically relatively small. Over here, the number of words we have in English are pretty big. So this is a much faster way of accessing your data than this. And so, because of that, tries can be very, very useful to store dictionaries of words and access them quickly and retrieve them quickly. We have actually messed around, bended with the Wikipedia thing that we were doing as a way of sorting things and other things. And as an idea of finding duplicates and keeping track. So suppose that you have, if you want to deal with keeping duplicates, so you want, like, you don't just care about what words exist, but how many of them we have. In your accept state, you can go ahead and add the numbers like 5, 2, 1, 3, and that means there's 3 memes, there's only 1 me, there's 2 cars, and there's 5 cats. And so you can do that to store duplicates without having to worry about extra space. But you could also do that in an array by keeping the frequency as well. So that's not that much of a gain there either. So how do you search through something? Again, it's like binary search, except here you can't just say less than or greater than. If you're looking here, you have to look at all the children and find out. And you should ideally try to keep them in an alphabetical order within this level, but you don't have to. In that case, you just have to traverse each of them to identify. So there is a little bit of a trick trying to get going here. It's not as clean as it may cut out to be, but it's still a very a good algorithm to talk about in 302, in my opinion, because I want you to realize that there's not just binary trees. Here's an example of something that it doesn't have to be ternary or binary. In fact, this case is binary, but it could actually be the size of the alphabet. So if you have 26 or 24 letters in your alphabet, it will more than likely be a 24-nary tree, because you will more than likely have at least one node that has 26 letters coming out of it, right? I mean, pretty sure that there has to be, probably with a vowel, you know, like a vowel could probably be followed by just about any letter, even other vowels potentially, but very likely you can get to that level. I don't know, probably like S, who knows? Anyway, so it's just to kind of open your eyes that there's just more to trees than just binary trees. What else do I want to say about that? It's very easy to implement, actually. You just gotta make an array of pointers for each of these. Instead of them being left and right, you make it an array of pointers. Kind of gets into the idea of graphs. And then yeah, we can talk a little bit about sparse tables. No, I'll let those for later. Sparse table. Yeah, I'll leave the sparse tables for when we talk a little bit about graphs. But yeah, that's pretty much all there's to it to try. You have your data. Doesn't have to be words. It can be sequences of characters or digits. And then you generate branches based on the next item in the sequence, and you draw it out. And then once you have the tree, if you need to have a way of identifying an accept state, which means that it is found, that it is not found. This is not useful for sorting because, again, this section may not be sorted. However, you can guarantee that if you're doing a traversal, that you're gonna print out all the things with C here and then all things with A, even if within this subcategory they're out of order. But we'll talk more about that when we talk about breadth first versus level versus depth first search. So yeah, I think that's just a good introduction to your tries. I recommend you check out the Geeks for Geeks on tries. And again, it's not going to be in the test. Maybe an extra credit. Who knows? Unlikely though. It's just so you're again aware that there is more to trees than just binary trees, which we always talk about. There's binomial heaps as well. That one is another example of trees that are more than just binary. All right. I'll see you guys in the regular lecture and have a good day. Don't forget to like and subscribe.